if you're doing a word problem and it talks about motion moving in opposite directions, like for example, two objects moving at the same speed start in the same time, move in opposite directions, or two objects start at the same point, or start at a certain point, a given distance apart, and then moving towards each other at the same speed until they meet. The distance the second travels will equal 1/2 the total distance covered, yada yada yada. So here's what that means. So in one case, they're starting, let's say one is going in this direction, and someone else is going in this direction, opposite directions. In that case, let's call this distance 2. Let's call this distance 1. In that case, the total distance is going to equal distance 1 plus distance 2. Makes sense, I think. Another scenario that you have is a couple dudes or dudettes are apart from each other and they are moving towards each other. Perhaps a little attraction pulls them towards each other, like magnets. In both cases here, once again, the total distance is going to be the distance of one of the people plus the distance of the other. If you have motion in the same direction, so like you got this person starting here, and you got this other person starting here. Person 1 starts early and they're going in this direction, and then it says, hey, person 2, they're going to start late, but they're eventually going to catch up to them. How long will it take them to catch up to each other? Well, in this case, the distance of each of the people, they have to be equal. If they're starting in the same spot and ending up in the same spot, that means that their distances have to be equal to each other. So keep that in mind. That's going to come up in some problems on the ACT for sure. All right, two cars leave a restaurant at 1 p.m. One is traveling east at 60 miles per hour. The other is traveling west at 40 miles per hour. At what time will they be 350 miles apart? So situation is they're starting at the same spot. One goes east, one goes west. The one that goes east, its rate is 60 miles per hour. The one that's going west, we'll call that rate 1. We'll call that rate 2, is 40 miles per hour. At what time would they be 350 miles apart? So once again, if we go back to this up here, if they're going in opposite directions, the total distance has to equal d1 plus d2. So if you recall, distance equals rate times time. Distance equals rate times time. These little subscripts that I have here have no mathematical value. It just tells you the first person and second person. Person going east is the first person, person going west is the second person. So we know that the total distance is going to equal distance 1 plus distance 2. We were told the total distance is 350. Distance 1, we don't know what it is, but we know it's rate times time. And we know that the rate is 60 miles per hour. We don't know the time. Distance 2 is the rate, which we know is 40. We don't know the time. Now those times must be the same, because they're both leaving the restaurant at the same time. How long will it be until they are 350 miles apart? So the times have to be the same. You combine like terms, and then divide both sides by 100. You're going to get 3.5. Time was being measured in hours for this, so they will be that 3.5 hours from now. It says at what time, not how long, not how much time, but at what time. So if we add that to 1 o'clock, we're going to get 4:30 p.m. Good? Good. Number 2. Gloria leaves home for school, riding her bicycle at a rate of 12 miles per hour. Let me just write down that information. So we got Gloria. The rate of Gloria is 12 miles per hour. That takes care of the first sentence. 20 minutes after she leaves, her mother sees Gloria's English paper on her bed and leaves to bring it to her. So now we got Mom. If her mother drives at 36 miles per hour, so the rate of Mom is 36 miles per hour, how far must she drive before she reaches Gloria? Now this doesn't tell us how far they drive. It also doesn't tell us the time. Here's what we do know. The time for Gloria, whatever that is, the time for the mom is 20 minutes less. So it's Gloria's time minus 20 minutes. I really don't want to write 20 minutes because we're talking about hours. 20 minutes is 1/3 of an hour. So I could say this. So once again, to sum up, because there's lots of things going on here. First sentence says that Gloria is going 12 miles per hour. The rate of Gloria is 12 miles per hour. The third sentence says that the mom is going 36 miles per hour. The second sentence says that 20 minutes after she leaves, her mother sees the paper and leaves. So that means however long Gloria has been driving, their mother will always have driven 20 minutes less. So since they're going in the same direction, that's what's happening here. We got Gloria and we got Mom. The distances are going to be the same. So the distance of Gloria is rate times time. The distance of Mom is rate times time. We can set them equal to each other. Same direction, set them equal to each other. The distance of Gloria, her rate was 12. Her time, let's just leave it as a t. And then the rate of the mom is 36. And the time is t of g minus 1/3. We're just using t. Well, I'll tell you what, let's get nuts here. Let's do t of g. So when we're done, we know this is the time of Gloria. So, using the distributive property, I'm going to make this smaller here so I got more space. Using the distributive property, if we multiply 36 here, we're going to end up with 36 t sub g minus 1/3 of 36 is 12. If we subtract 36 t sub g from both sides, we're going to get negative 24 is the time of Gloria, equals negative 12. If we divide both sides by negative 24, we get the time of Gloria is going to be a half. Talking about time, talking about hours. So Gloria drove for half an hour. Does that answer the question? No. How far must she drive before she reaches Gloria? Well, we know that Gloria's distance and her mother's distance have to be the same because they're meeting up with each other. Let me label the order in which I did these things. Anytime you do things in an unlogical way on your paper, you want to label the order in which you did it. So to figure out the distance that they traveled, we're going to take Gloria's rate times the time, and we're going to end up with 6 miles. They both traveled 6 miles. Answers the question. Let's move on. Nisha, beautiful name for a boy or a girl, leaves home at 11 a.m. and rides to Andrea's house to return her bicycle. She travels at 12 miles per hour and arrives at 11:30. So let me write down some of this information. We got Nisha, so glad to meet you. Saw you in the school hall, talking to a teacher. The rate that she rides her bike, 12 miles per hour. Took her half an hour to make that trip. So her time riding her bike is 30 minutes. In hours, that's half an hour, or 0.5 of an hour. Then it says, tell you what, instead of Nisha, so glad to meet you, let's just say bike. Then it says that she walks home. We do not know her rate of walking. We do know that her time for walking, though, she left at 11:30 and got there at 1. So that would be an hour and a half, or 1.5 hours. So it's the same distance. She starts at her house, goes to Andrea's, and then goes from Andrea's back home. So we know that the distance that she bikes has to equal the distance that she walks. Distance is rate times time. So she went 12 miles per hour for half an hour. The rate at which she walked, we don't know, but we know she did it for 1.5 hours. So this is 6 equals the walking rate times 1.5. If you divide both sides by 1.5, you're going to get 4. So she walked for 4 miles per hour. That was her speed. Direct variation. Mentioned this in a previous lesson. Didn't use it much then in that, but we are going to use it here for sure. Direct variation essentially means that you can use a proportion to solve problems. If two things have direct variation, that they move both in the same direction. As one gets bigger, so does the other. The more I eat, the more calories I eat, the more pounds I weigh. The more I run, the less I weigh, both moving in the negative direction. So direct variation is relationship of x with y is going to equal the second relationship with x with the second relationship of y. All right, so example 1. X varies directly as y squared. Well, we can simply write that as x over y squared. And x equals 12 when y is 2. So that's going to be 12 over 2. what is the value of x when y is 3? So we want to know what x is when y is 3, and the relationship is supposed to be squared. So it's 3 squared. And I don't have my 2 squared here. So since they vary directly, x varies directly as y squared, and then we're given x and y values, essentially the relationship that we're given is this. It's always going to be x over y squared, and then we're told that these pairs go together. X is 12 and y is 2. And then these two go together. We don't know what x is, and we know y is 3. So it's x over y squared equals x over y squared. It's direct variation. So it's going to be 12 over 4 equals x over 9. 12 divided by 4 is 3. If you multiply both sides by 9, you're going to get x is 27. Wonderful. Inverse variation means that the numbers move in opposite directions. So instead of having the relationship of that we just had x1 over y1, we're going to have x1 times y1 and then x2 times y2. So direct variation, you divide things that are related to each other. In inverse variation, you multiply them together. Let's see how this works. The time t, by the way, distance problems are indirect or inverse variation, because if you're going a set distance, the faster you drive, as that number gets bigger, the smaller your time is. Or if the time gets bigger, that means that your driving rate has to get smaller. So that's an example of an inverse variation. The time t to empty a container varies inversely with the square root of the number of men, m, working on the job. So that's saying t times the square root of the number of men. That is our relationship. If it takes 3 hours for 16 men to do the job, so 3 hours, that's the time, times the square root of 16 equals, how long will it take for 4 men, 4, working at the same rate? I wrote that backwards. Time is first. We don't know what that is. 4 men. So in each case, we got the time, 3, and we don't know. We got the men, 16 and 4. Simplifying this, square root of 16 is 4. Square root of 4 is 2. This is 12 equals 2t. Divide both sides by 2, and you get t is 6. T is measured in hours, so it would take 6 hours for 4 men to do the same job as that's right. So it takes 3 hours for 16 men to do the job. It's going to take 4 men working at the same rate to do it in 6 hours.